Hello, welcome back to the course Aerospace Structural Analysis. Today is lecture 10, the last lecture of week 2. Here also we will continue with membrane analogy and we will primarily talk about torsion of shaft with narrow rectangular cross section using membrane analogy. So, before we move into narrow rectangular cross section shaft, let us talk about the corollaries of the membrane analogy. In the last lecture, that is lecture 9, we talked about two corollaries of the membrane analogy. The first one So, in the last lecture, the first corollary that we studied was that if we have a shaft with arbitrary cross section and if we select any point on the cross section P, then the resultant of the shear stress at that point P is 0 in the direction tangential to the contour passing through that line, and the entire resultant is in the normal direction to the contour of that analogous membrane passing through the point. So, in other words, if we have a shaft, we need to find out the resultant of the shear stress at any arbitrary point P, then we have to imagine a contour line passing through that point P in the analogous membrane, and the resultant of the shear stress in the direction tangential to this yellow color contour line is going to be 0. So, tau in this direction is going to be 0 and this would be the tau resultant. So, the yellow colored line is the contour line is the contour line of the analogous membrane. So, in other words, we can say that if we are given a cross section with an given a shaft with an arbitrary cross section and we are asked to find out the resultant of the shear stress or the net shear stress at any point P, then we have to think of the contour line passing through that point P on the analogous membrane, and then the resultant of the shear stress is going to be 0 along the tangential direction to this contour line, and the entire resultant is in the direction of the normal to the contour line at the point P. So, this was the first corollary that we discussed. The second corollary that we discussed is that the resultant shear stress, that is tau r or tau r, which is in the normal direction, the expression for tau r is given as d phi by dn. Now, phi is analogous to W or the out of plane deformation of the analogous membrane. Therefore, d phi by dn is analogous to the slope of the deformed membrane at that point P. Therefore, tau max is obtained when d phi by dn is max and that it happens at a point where the slope of the deformation is maximum in the analogous membrane. These two corollary were discussed in the last lecture and also derived. The third important corollary that we need to keep in mind is that for a shaft with arbitrary cross section, we have seen that the expression for the moment or the torsional moment mt can be written in terms of Prandtl stress function as 2 into phi into dx by dy. This we have seen when we were discussing about the Prandtl stress function. Now, since phi is analogous to the out of plane deformation W, since phi is analogous to W or the out of plane deformation of the membrane, therefore, this is analogous to finding out. So, this is analogous to 2 into W into dx dy. Now, W into dx dy is nothing but the volume made by the deformed membrane along the xy plane. So, this is nothing but 2 into volume enclosed by the deformed membrane. Therefore, to put it in other words, if we can imagine the analogous membrane and imagine the deformation of the analogous membrane, then the volume enclosed by this deformed analogous membrane is equivalent to the double area derivative of the Prandtl stress function, and therefore, it is equivalent to the expression for the torsional moment. So, if we can find out the expression for W, or even we can visualize the expression for W, we can obtain the expression for the torsional moment by just finding out the volume enclosed by the analogous membrane into 2. So, this is also an important corollary to easily obtain the expression for the torsional moment by imagining the deformation of the analogous membrane using the concept of membrane analogy. So, by using these corollaries that we have discussed so far, we will be solving a very important application of membrane analogy, which is very much pertinent to aircraft structure. So, the next topic that we are going to discuss is torsion of shaft with rectangular cross section, with narrow rectangular cross section. So, this is what we have. So, we have this rectangle, we have this shaft whose cross section is a narrow rectangle. So, the longer dimension of the cross section is B and the shorter dimension or the thickness is T, and we have this criteria that B is much greater than T, which kind of defines that the cross section is narrow. X and y are the in plane coordinate axis and z is the axis along the length of the shaft. To make this even clear, let us understand that this cross section, this shaded portion that we have done, we have drawn, is nothing but the cross section of a shaft. So, we have a shaft, and if we take an arbitrary cross section, it is how this looks. So, this shaded portion is the cross section of the shaft and not the shaft itself. Now, let us try to solve this problem of torsion of this cross section by using membrane analogy. So, what we are going to do? We are going to find out the torsional rigidity of this cross section. We are going to find out the expression for shear stress of this cross section, and we are also going to find out the expression for maximum shear stress of this cross section. Now, let us start with finding out the Prandtl stress function for this cross section. Now, in order to, if you try to find out the Prandtl stress function, you will see by the conventional approach that del 2 phi by del x square plus del 2 phi by del y square is equal to minus 2 g theta, and phi is constant or 0 along the boundary. You will find it extremely difficult to solve the problem, but the problem will become very easy when we adopt membrane analogy. Now, let us imagine a membrane of this shape, exactly of this shape. Let us consider a thin membrane which is of the shape of this thin rectangular cross section with one side as B and the other side as T. Now, let us imagine all the forcing and boundary conditions on the membrane as we have discussed later. Now, imagine how the deformed shape of the membrane is going to look like. Let us try to first visualize that how the deformed shape of the membrane will look like under all the boundary conditions and the loading that we have explained earlier. Now, if we imagine, if we try to visualize, we will see that the deformed shape of the membrane is going to look something like this. So, the green color line shows the deformed shape of the membrane in the YZ plane. It is very easy to visualize the deformed shape of the membrane. So, the deformed shape of the membrane, because it is very narrow, is going to be like this in the YZ plane. Similarly, it is, if I try to draw the deformed shape in the XZ plane, then it is going to look something like this. It is going to look like this in the YZ plane, XZ plane. right. So, in the yz plane the deformed shape will be mostly flat except a quadratic or parabolic kind of shape at the two ends of the cross section, and on the yz plane it's going to be a quadratic function or a parabolic kind of function that I have drawn. Now imagine this deformed shape, and let us try to figure out the Prandtl stress function from this. So, Prandtl stress function is analogous to this deformed shape that I have drawn using green color. So, from this green color shape, let us, which varies in xy plane, let us try to imagine the corresponding Prandtl stress function. Now, let us make some assumption. So, we are trying to find out from the deformed shape of the analogous membrane. Now, if we try to imagine what, let us, before we imagine, let us first try to approximate this deformed shape. Let us try to make a practical approximation of the deformed shape. So, this is the actual deformed shape of the membrane. Now, let us try to approximate it. Now, what I have done, sorry, let me, this has become bigger. So, now what I have done, I have, so my actual shape is like this. It is flat for most of the region, and at the last end part it is parabolic. What I have done is that since this is a narrow cross section, since B is much larger than T, I have approximated this shape. I have approximated this shape by this shape. I have neglected the end effect and I have removed the parabolic part just at the end and approximated by this flat, entirely flat deformed shape. Though this is an approximation, but this is a very good approximation without much loss in accuracy, because the parabolic portion will be only at a very small region near the end, and if we approximate it by a flat region, we will not face much change in the accuracy of the calculation. So, if we now proceed to find out the Prandtl stress function based on the approximated deformed shape of the membrane, then we can say that the Prandtl stress function phi can be written as a function of x alone, and it is not a function of z because I have removed the end effect. So, neglecting the end effect, so the deformed shape is constant, approximated deformed shape is constant and it is not changing with y. So, phi can be approximated as just a function of x, and since it is just a function of x, we can say that d2 phi by dx square is equal to minus 2g theta. So, this is coming from the expression that del 2 phi by del x square plus del 2 phi by del y square is minus 2g theta, and this is equal to 0 since phi is not a function of y. So, how are we coming to this conclusion? We are coming to this conclusion from the actual deformed shape of the membrane, analogous membrane, which can be fairly approximated by a shape which is not dependent on the y coordinate. Now, therefore, this is a good approximation that we have made, which will make our calculation much more easier. Now, if we try to solve this equation, we will get phi as minus g theta x square plus c1 x plus c2. So, if we solve equation 1, okay, so we get equation 2 by solving equation 1. Okay. So, now we have two constants C1 and C2. We have to find the values for C1 and C2. Now, using boundary conditions, we can find C1 and C2. So, what are the boundary conditions? The boundary conditions are that the Prandtl stress function phi is equal to 0 at x is equal to plus minus t by 2. So, since the membrane, analogous membrane is fixed on the boundary, analogous membrane is the deformed shape of the membrane is analogous to say phi, we can say that phi is equal to 0 also on the boundary, which is given by x equals to t plus minus t by 2. Now, by imposing this condition, we get 0 equals to minus g theta t square by 4 plus c1 t by 2 plus c2. Similarly, we get 0 now from this two equation we get c1 equals to 0 and c2 is going to be g theta t square by 4. Now, if we substitute this, then phi x turns out to be minus g theta x square minus t square by 4. So, this is the Prandtl stress function that we have obtained by solving from the approximated deformed shape of the membrane. Now, we will try to find out how the shear stresses can be obtained from this stress function and how the torsional rigidity of this membrane can be found out from the this stress function that we have derived. We will carry that on in the next lecture on this topic. Thank you.